Do you know how to get best context from vector DB? And what are the retrieval algorithms in RAG? So in this video, I'm explaining you all of this. So hi guys, welcome to Freebirds 2 and welcome to RAG playlist, in which I teach you about RAG and LLM with different domain projects from basics to advanced level. This is the part 4 of the playlist, in which I explain about retrieval process in RAG that find the perfect context for your query so that LLM can provide the correct response even if the LLM has not trained on that data. So in between, I also showcase all the techniques and algorithms used in retrieval process along with the Python code and also optimization to enhance the context via ranking and applying the similarity measures or models or LLMs as well. So let's get started. So first question is, what is retrieval in RAG? Retrieval in RAG is the process of fetching the relevant information or context from external knowledge base or vector DB to assist in generating the accurate or context-aware outputs. So if your LLM is not even trained on that kind of information that you want to get from LLM, with the help of RAG, you can get it. So the retrieval stage is critical, but it directly impacts the quality and relevance of the final response that you get from the LLM. So do you know how the retrieval get the perfect context? So the answer lies in the RAG find the perfect context for a query using various techniques and algorithms. So here are the glimpse of that. We use the vector based retrieval system that use the similarity metrics like cosine similarity, Euclidean distance type of thing, and we use the sparse vector retrieval techniques. We use the hybrid retrieval techniques and along with the neural retrieval techniques as well. And after the initial retrieval, ranking algorithms are applied to refine the order of the results, and those kind of ranking algorithms are like point-wise ranking, pair-wise ranking, or list-wise ranking as well. We can also use semantic ranking as well. Okay, so these kind of things can help you to get the best context for your prompt. And there is also one more point that you can also optimize it further as well. So to improve the retrieval efficiency and relevance, several techniques are used. You can also try to use tokenization. You can also use stop word removal, lemmatization, indexing as well, and along with the many kind of algorithms as well. And all these things will help you to get the best context. So now let me show you in the Python notebook that how to apply every of this technique on the different kind of data. We are using the LangChain along with the ChromaDB and apply all the techniques and algorithms one by one. So here is the code, guys, that you see the retrieval in RAG. We are implementing the retrieval process that will fetch the query along with the this context, and that context will help you to get the perfect response from the LLM as well. So we'll start with the vector based retrieval that use the similarity measures kind of technique, that is your Euclidean distance, Manhattan distance, cosine similarity kind of things as well. We'll first start the LangChain and along with the our other dependence libraries as well. Okay, you should try to read this because this is the information about the vector based retrievals. And let me start you with the code. So we have this kind of a model, a simple model for the embeddings, and we will build an embedding model here, and we will have this kind of data that we have, and we will fill that kind of data into the FAS. FAS is a kind of a vector DB that we have. Okay, and we will first convert the document to embeddings, and we'll do like this. Okay, and you should know that the FAS always use the Euclidean distance as well to find the similar kind of context. Okay, so here is the we build in that, and then we store a FAS index here, and this is how it build the FAS index. And when we put a query and ask it to and embed the query as well, and we will compare the embeddings of the query with the embeddings that are already present in the vector DB and find the similar kind of embeddings, that is top 3 embeddings. It will give us this kind of result. Okay, with the document and the distance as well. So that is the most good response that we have. But if you want to try with the cosine similarity, you just have to use this kind of code. Okay, so we'll try to do the L2 distance or the Euclidean distance with this is code, but for the cosine similarity you have to normalize it. Okay, so that's why we use this code to normalize it, and also this code to normalize it as well. So in that way, if you just add these 2 lines of code, it will use the cosine similarity and give you the result according to that. Okay, So now let's go to the next thing, that is called sparse vector retrieval. So sparse vector retrieval use the two techniques, that is called TF-IDF and BM25. Okay, BM25 is called best match 25. So these two kind of terms are used in the sparse vector retrieval. And if you don't know about what is sparse, so sparse means that kind of a matrix that has zeros and ones as well. Okay, so you know already about that what is TF-IDF because I explained in my previous videos. It is a statistical measure used to evaluate how important a word is to a document within the collection. It assigns higher weights to a words that are unique to a document while downweighting the common words like the, is, am, are, like these kind of words as well. Okay, so and the BM retrieval is kind of a ranking function that commonly used for document retrieval. It is a statistical algorithm that balances term frequency and the inverse document frequency and the document length normalization. These factors make BM25 efficient for the keyword based task. So if you have some kind of a word and you want to search, then that time this kind of a BM25 retrieval is the best as compared to the TF-IDF as well. Okay, so for first thing we will start with the installation of these kind of libraries as well. These are our documents that we use, and we first try to do it with the TF-IDF. Okay, this is our simple query that we have, and we need to find the answer for this, and we know that the answer is this. Okay, the third line. So let's try with the TF-IDF. So first we load a vectorizer, and then we have to transform it. We have to make it in the sparse matrix as well, because in the sparse matrix way it will know that which has the more weight, which has the less weight as well. And then we compute the cosine similarity. The cosine similarity will compare our documents and our query as well. Documents are here and query are here. So in that way it will give us the response. And similarly for the BM25 retrieval, we use the same thing. First we tokenize the text, and then after the tokenizing we apply the BM25 model on it, and then after the BM25 model we tokenize our query because we have the query as well, and then try to compare it. Okay, and after the comparison we just return the results. So the TF-IDF results will return this kind of result with this kind of TF-IDF score, and that result is correct for the top one, and along with the BM25 this result is also correct, and it gives a more score to this. Okay, so that's how you can try to apply these two kind of techniques. That is totally based on what kind of use case you are solving. Okay, and next we have the neural retrieval models. So the neural retrieval models, they use the frameworks like transformers and LangChain as well. Okay, these methods demonstrate the dual encoder models, that is called DPR as well, or the cross encoder models, or the ColBERT kind of models that use the BERT. Okay, so the first thing is called dual encoder model. A dual encoder model is a neural architecture model that is designed for the retrieval task. It independently encode the queries and documents into a dense vector representation, so that we have like a very easy search. That is a very also it is a less computational expensive as well. Okay, so unlike the traditional methods that we use above, that is BM25 or TF-IDF, dual encoders focus on the semantic similarity, because here you see that we don't use any kind of semantic similarity here. We just try to use the words, that what kind of words are comparable, what kind of words are comparable not. Okay, that's why it more aligned toward the semantic similarity. That's why it will give you much better response as compared to the BM225 or this TF-IDF as well. Okay, in that way you can use it in the FAQ systems or document search systems or knowledge based question answering systems as well. Okay, the first thing we try to load, that the DM question encoder, it's tokenizer, context encoder, and context tokenizer as well. Okay, we load everything. These are the documents, this is our query. So first thing we try to make the query embedding as well. We make the query embedding. The first thing is we tokenize it, and then we encode it, and same thing we do for our context. This is our context, right? So we do it same thing with context encoder and context tokenizer. We make a list, and when we make a list we try to use the FAIS, and FAIS use the approximate nearest neighbor search, that is also called as the cosine similarity, that we use here to find it. And in that way we'll try to find the best answer for it, and as you see the best answer is right. Okay, and in that way you just need to focus on what kind of search you want to do. You want to do the keyword based search or just only the word based search, so then you can easily use the BM25 and TF-IDF. But if you want to use the semantic search, you need to know the context and the meaning of the sentences, then you have to use the dual encoder models as well, or DPR models as well. Okay, And then next is we have to visualize it. As you see that this is our query and these are our the context. As you see that this is the more closer to as compared to these things. So that is the this is the like perfect answer that we have. So in that we can also try to visualize your responses to get the best output possible. Okay, next is called the cross encoder models. The cross encoder model is a it use the query and the document together. It just process them together and evaluate their relevance as well, that how these two things are relevant. So this approach use a neural network to jointly encode the query document pair and enabling a fine grained scoring of relevance. Okay, so how it completely works. Okay, so let's take an example. We have the pair 1, we have the pair 2. Okay, when we encode, a transformer based encoder is used like BERT and anything like that, and it will pair them simultaneously. Okay, the query and the document are treated as a single input separated by a separator token. Okay, then we have to get the fine grained relevance scoring, that how these two are relevant. So the pair 1 is more relevant and pair 2 is less relevant as well. So the joint encoding allows the cross encoder to capture the nuanced relationship between the query and the document, such as the contextual overlap, like AI/ML in both query and document 1, and misalignment, like backend development in document 2 that does not match the query. Okay, so we have the query, we have the response, both things in up there. So that's how we do it. Okay, so we have the query like this. The software engineer role is a AI/ML domain role. So that so you have to compare this to these kind of things, and it will generate a score around that based on the words that I have. So that's why the pair 1 get the more score, because it has the contextual overlap as well. It don't have any kind of misalignment as well. Okay, so in that way try to rank them. So as you see the cross encoder model, it try to rank them and make predict them as well. It will give you more score to this kind of document as well, this kind of context as well. Okay, that's how this thing will work. Okay, now next thing is we have the ColBERT model. The ColBERT model is a contextualized late interaction model over BERT. It is a retrieval framework that is designed for the efficient and fine-grained token level interactions. It works on the token level between the query and the document. So it also capture the semantic meaning here, and it maintains the token level embeddings. Okay, so it's like above we use, so we there use the sentence level embeddings as well, but here it use only the token level embeddings, enabling the precise matching and the relevance scoring. Okay, so it works in the same way. It first do the token level embedding rather than the sentence level embedding or the paragraph level embedding. Then it instead of collapsing the embeddings into a single vector, ColBERT compute pairwise similarity between the query tokens embedding and the document token embedding. So in that way, it helps to find the best response possible or the best context possible for your query. Okay, then it apply a maxim operation to aggregate the result so that it can have the maximum similarity score across all the tokens. Okay, so let's take an example here. So let's say we have this kind of like query, and this kind of query will have this kind of two docs. So for each kind of word, it generates some kind of a score. Okay, and some kind of score is there. So at the end, it just take a sum of all the scores and sum of all the scores, and then compare which score is maximum between these two kind of documents as well. Okay, so in that way it will try to give the best response possible. Okay, so as is here, it first embed the query, embed the docs, and calculate the maximum score here, and then give us the maximum score possible. So you see the document 2 has the maximum score. That means the document 2 is more relevant or the best context for our query as well. Okay, so these are like key highlights that use the dual encoders for the it encodes the queries and documents independently, but the cross encoder it join them and then compare them. It is efficient for the large scale retrievals. It is efficient for the it is more accurate, but it has a slower due to pairwise computation, and it is suitable for the high accuracy task where you need the more accuracy as well, because it use the token based embeddings as well. Okay, and then let's talk about the ranking algorithms. So these kind of ranking algorithms helps, like when you have these kind of responses, like you get the three, like let me give you example here. Let's just say you get a three kind of top searches from here, like this kind of searches you got. Now you want to rank them based on the context and based on the user behavior and user history as well. So these all kind of things are required here, right? So you want to rank them, that what kind of context is more aligned to the user need, not on the basis of the context that we see between the query and the document. Okay, so that's why here we use like many kind of machine learning models or the large language models as well. So first thing is the point wise ranking. So point wise ranking is a machine learning approach that predicts the relevance score. Okay, that predicts the relevance score of an individual document relative to the query. Each document is treated independently, and the model is trained to estimate how relevant each document is to a query on a basis of a logistic regression model. So for example, let's take an example of the e-commerce platform. Okay, you search for a wireless headphones, and the goal is to rank a list of product, how relevant they are to the search query. Okay, so the first thing that it do the query document similarity, textual similarity, product features like price, reviews, ratings, and brand reputations as well, and then query product interaction. In all these things are taken into concern, and then we get a rank on base of that. Because above, if you see in these kind of algorithms that we use above, we only have the meaning of the context, meaning of the semantic meaning, but we don't take care of other things. So here the other things are also being taken care. The similarity score is there, that we already know that above we always have a score above, but here the other things are present like price, rating, label. So price and rating are also relevant here, that how much relevant they are to this kind of query as well. So on the basis of that, we build a machine learning model, and it will predict the answer, that what kind of product are more likely to be shown on the top. If I just give you an answer that why we don't use the similarity score alone, because a similarity score evaluates only the textual or semantic meaning between the query and the document. It does not account for the important factors like price, rating, popularity, or the user preferences. So the feature like price rating may influence the relevance in a non-linear way. So a cheaper price may not always mean or more relevant product if the rating is low, and higher similarity score might not always outweigh the higher price. So these kind of things you have to be taken care. So that's why these kind of things required to build a best ranking algorithm. Okay, then we have the list wise ranking that use a combination of lambda rank. It is used the gradient boosting technique, and the MART, that is called multiple additive regression trees. So these kind of multiple algorithms are used to rank those kind of documents or those kind of answers that we get from the large language models. Okay, so here we see these are like real life example that a user put a query that best electric cars 2024. So these are the documents that we have. So based on that, it just tries to put a mark that what are the relevance that they have. So document 1 relevance is equal to 5, that is the highest relevant, then 4, then 3, then 2, and 4. So in that way, these are ranked on the base of like a tree based algorithms that we have, and we have multiple parameters as well. Okay, and it will calculate the score on the base of that, and that score will kind of rank them or kind of order them in that form as well. So here we use the XGB ranker model. Here we have all these queries, we have the our query, we have our document, we have the labels, and based on that we do the same thing. We first vectorize our documents, and then we use the XGB ranker, we use the pairwise ranking. Here we predict the rank. So here how it predicted, you see what is natural language processing, it predict the rank very correctly, that NLP, the answer is here. So that's how you can rank with the help of XGB ranker, that it used the two algorithms, and it is kind of much better than in not just only identify like which documents are relevant, but also ensuring that the most relevant documents also appear in the top results. Okay, That's how to do it. And then we have the semantic re-ranking. In the semantic re-ranking, it uses the large language models. That on the basis of the large language models, those large language model will rank rank your context, like multiple contexts, give them some kind of rank as well. Okay, so here we use the a small kind of large language model. Here we have this our query, we have these other documents. We just like apply this kind of large language model here and try to apply the re-rank algorithm here. It will give the result. Okay, so that's how you can use a simple large language model to rank them. Okay, and then we have the retrieval optimization techniques, because that's you do a retrieval and rank them, but how to optimize this thing. So that's you can do with the simple techniques that we use in our NLP as well. That is the you can try to pre-process the data, remove any kind of stop words, and also lematize the text as well in while you are like putting the data into the vector DB. Okay, and then we can use the sparse retrieval as well, because if you don't know, the sparse retrieval is a technique that where the index only stores the non-zero or relevant information. There is no zero value is there, so it calls a sparse because in many cases the data is sparse, meaning most of the element in the documents are either irrelevant or zero as well. So this inverted index is a fundamental data structure used in the sparse retrieval, especially in information retrieval such as search engines. So here we use the inverted index, and inverted index is an index data structure that is used for the full text searches. It maps each word or term in a document collection to a list of documents that contain that term. So you don't actually searching the whole document, you are just only searching a small list that this kind of word is present in these kind of documents. So you only go to these kind of documents only. Okay, so let me just give you a small example here, that we have these kind of docs. Okay, and we create a inverted index. Okay, the inverted index will try to put all the kind of unique kind of words into the list, that we have this list, that set word is present only in the list 0, that is only in this, and the cat word is present in the list 0 plus 2 as well. Okay, and the word is present in 0 and the 1 as well. So in that way it try to mark them. So when it try to mark them, it is very easy for us to search that what kind of documents we need to search, and it is easy for us to get the correct response in the less time. It has less computationally expensive as well. Okay, and then we have the other terms that we want to search in the inverted index. We can easily search because we know that at what place these two words are. It is very faster in that way. Okay, so that's how you can try to do it. That's how the retrieval, their ranking, their pre-processing will work. And I hope you completely enjoyed this kind of video as well. And in our next video, we'll learn about a project that is called GenAI and RAG tutoring system, and in which we build a complete end-to-end app using GenAI and RAG along with LLMs that will help you to learn anything from scratch by using a RAG kind of a framework. We have to make it kind of a personalized tutoring system with a feedback loop that can also track your progress, track your learnings as well. We make a complete kind of a product in that project. Alright, so just be with it. And if you want to learn more about generative AI, prompt engineering, and data science and machine learning, you can watch my video on YouTube. I'll also read my blogs on Medium. We'll be in our next video. Thank guys. Thank you so much.